se escucha en mi computadora.
¿Ustedes pueden ver la pantalla?
Sí.
Ok. Hola a todos, soy Takasuka y mucho gusto conocerles hoy. Esto es un poco sobre mí. Soy de Orange County.
No, sí está bien, puede continuar. Sí, todo bien. No, sí, todo está bien, sí lo podemos oír, solamente que queremos transmitirlo en las bocinas y no nos puede, entonces por eso, pero sí lo estamos escuchando, no se preocupe. No, es que estamos en una audiovisual, por eso.
Um, Puedo pasar por estos dispositivos si quieren saber exactamente en cuáles proyectos he trabajado, pero no sé si toda la evidencia um, ha trabajado con eso y sabe que es diseño asistido por ordenador. Así que estoy preguntando, ¿ustedes quieren saber qué es y cuáles son los diferentes tipos de como impresión 3D? Okay, I'll just keep talking, I guess. Ok, se puede usarlo para diferentes contextos, por ejemplo, en la arquitectura o en la ingeniería. Um, y cuando hacemos los objetos que diseñamos en la vida real, dos maneras que podemos hacerlo son impresión 3D y molde de inyección. Y realmente para los prototipos iniciales usamos impresión 3D. Y la resolución es peor, pero es muy fácil hacer un objeto que diseñamos cuando solo queremos probar cómo es, porque muchas veces necesitamos cambiar cuál es el diseño. Y cuando ya hemos decidido en cuál diseño que queremos usar para un producto, algo así, y queremos hacer muchos de los mismos productos, entonces muchas veces es mejor usar molde de inyección. Otras veces para prototipos de un paso más avanzado, y es resolución mejor. Básicamente en molde de inyección tenemos un molde y vamos a inyectar algún material. It's going to harden y entonces tenemos la pieza. Mientras que impresión 3D va a imprimir el objeto like layer por layer. En dos tipos de impresión de 3D que yo sé son de filamento y de resina. Filamento es resolución peor, but it's easier to print something faster usually with poor resolution. And what that means is like each layer has a certain thickness, or that like the edges might be kind of jagged. Pero con resina, we can have better resolution. And so that's, he usado primariamente impresión 3D con resina en mis diseños y productos o proyectos. It's a bit more messy because you end up with this, you end up with your object in the resin, and you need to put it in alcohol baths afterwards because this resin is very sticky and it gets everywhere. Así que esto es una ventaja de filamento en comparación con resinas. Después de que has imprimido la de filamento, no hay muchos pasos después antes de que puedes usar el objeto. Pero con resina se necesita esperar y poner el objeto en alcohol para lavar la resina del producto. Ok, así que aquí son los proyectos en que ha trabajado que usan el diseño 3D por ordenador. Y quiero preguntar si hay alguna que les interesa más. Así que aquí tengo un poll. Y no sé si va a funcionar. Ok. ¿Dónde está? Stop share. Ok. Así que ustedes pueden responder a este poll por este enlace web. Aquí también tengo el QR code aquí. O también se puede usar mensaje de texto, creo. Y entonces cuando votan puedo ver las respuestas. O si es más fácil, entonces tal vez ustedes pueden decirme como con cuál proyecto puedo empezar. Oh, I need to activate it. Creo que funciona ahora.
El código QR está muy pequeño y no alcanzamos a, a votar. Pero si quieres, le podemos decir cuál les interesa más a los aquí, de los que están aquí presencialmente.
Creo que
Sí, ya
no
me
estaba
lo
activado.
okay. El QR no se puede ver, es que está muy pequeño, pero no sé si quiera que aquí presencialmente le podamos decir que están más interesados pues nuestras personas, los videntes.
Ok, entonces tal vez se puede votar por mano y entonces decirme cuál es la más interesante.
Ajá.
Ok, um, entonces puedo regresar a la presentación si esto sería más fácil. Ok,
Me dicen que la de diabetes, la primera.
diabetes. Ok, cool. Oh, that's right. I did make a once intro slide on this one. Okay. Okay. En el segundo laboratorio que hice investigaciones fue en UCI, University of California, Irvine, en sur de California, y ellos hicieron investigaciones en la diabetes tipo 1. Hay dos tipos, pues algunos dicen que hay más, pero se enfoque más en diabetes tipo 1 y diabetes tipo 2. Y la mayoría de las personas que tienen diabetes tipo 2. um, pero las personas que tienen diabetes tipo 1 es muy diferente y los pacientes con la diabetes tipo 1 no le gustan cuando se mezcla con personas con diabetes tipo 2. Tipo 2 pues en ambos es que tienen problemas con la insulina y el azúcar en la sangre, pero tipo 2 se puede prevenirla con hábitos saludables, mientras que el tipo 1 no se puede prevenir. Y ellos creen que es algo genética que causala. Y lo que pasa con las pacientes con la diabetes tipo 1 es que sus células pancreáticas son destruidas por su sistema inmunológico y no pueden producir la insulina. Pero es necesario comer y um, um, en processed sugar, azúcar, um, para like basic things in daily life. Así que ellos se necesitan inyectar insulina cada día para que no estén enfermos. And if they don't, then su nivel de azúcar en su sangre aumenta mucho y entonces necesitan ir al hospital porque no se sienten bien. Tienen productos para ayudar con su insulina, su nivel de insulina y saber cuál es su nivel de azúcar en su sangre. Así que lo más básico es como inyecciones como pero hay como Dexcom, por ejemplo, es el producto que mi amiga con la diabetes tipo 1 usa. Y esto se puede monitorar su nivel de azúcar en su sangre constantemente sin necesitar like poke your finger throughout the day. And so hay un aguero que es constantemente en su cuerpo, pero the tip of the needle is not pointed, so it doesn't hurt as much continuously than if you were to like keep poking yourself with a sharp needle. And then you can also, and then there's another device that you use that will inject the insulin. So ideally, they're hoping that you can just have one device so that you don't need to poke yourself twice. One with a device that's monitoring your blood sugar, and then another one that is injecting insulin. But currently, that's the best standard of care. And these devices cost tens of thousands of dollars, which is ridiculous. They're probably cheaper in Mexico, but this is how it is in the United States. Okay. So one crazy idea that they have to cure type 1 diabetes, or I should say the lab that I worked in, was to use engineered cells. Okay, let me pull up where the engineered cells. Okay, so here's one of the papers. So I was working under a PhD student while I was a high school student. And she would have human stem cells, or no estoy segura en cuál parte ella había obtenido las células. Es posible que otra persona había obtenido los stem cells y convertidolos a human or pork, I think is porcine, islets. Así que ellos son los tipos de células de las células pancreáticas que se producen insulina. Y es posible que tal vez en el futuro, en vez de hacer inyecciones, que podemos una vez inyectar estas células en el cuerpo y que estas células van a producir el nivel de insulina que la persona necesita, que la persona con diabetes necesita. El problema es que cuando inyectamos estas células, no hay un vasculature network, so they're not supplied with blood very well, y se mueren rápidamente. Así que hay diferentes maneras que tal vez podemos salvar las células para que se puedan sobrevivir para más tiempo. Algunas de las maneras son nanoencapsulation, microencapsulation, or scaffolds. And the lab that I was a part of was focusing on a particular type of scaffold. Se puede ver el nuevo artículo, ¿verdad?
Sí, sí se puede ver.
Así que lo que ellos hicieron para hacer su scaffold fue usar el diseño 3D. So they printed out these molds using like the negative mold of what they wanted, usando impresión 3D de resina. And then they put silicone into these molds. You can't 3D print silicone. So that's why they wouldn't just 3D print silicone. You have to, silicone's like a polymer, and then it'll set after you've mixed a couple of solutions together. So you mix a couple solutions together, you put it in this 3D mold that they've created, y entonces ellos hicieron pruebas en ratones, which is controversial. You have to get ethics approval before you're doing it. But basically, it's because we don't want to start implanting these in humans first. You want to start with mice. So at first, they were just seeing how the scaffolds would react after they were implanted in mice with no cells to begin with, and whether blood vessels would innervate these slits. And so hopefully, because they were hoping that blood vessels would go into these slits, and then therefore that the pancreatic cells would survive and thrive. And there's a lot of things we don't know about this. So for example, one thing that they wanted to test, so they wanted to test how much innervation there was, and you can use histology to determine where blood vessels are, where certain types of tissue are. And you can also use immunohistochemistry to determine where the nuclei are. I'm not sure on the top of my head what ASMA and S100 are. Mature blood vessels. So you can look at the mature blood vessels here, and you can characterize them by how wide they are, how big they are, how much area they're taking up. So for example, like it might be better in some contexts to have more smaller blood vessels, but in other contexts, you want fewer big blood vessels. And so they kind of have to decide like what type of blood vessels they would like. And they were also testing the width of the slits, I believe. That's what they were saying in these different, okay. Yeah, so they tested different widths of these slits, 150 microns, 300 microns, 500 microns, and 1500 microns to see which ones had the best innervation. And so it kind of looks like with these 150 micron width slits that they're not getting great tissue growth and probably not great innervation. So likely the cells would not survive in this scaffold, but it might be more likely with 300 or 500. Yeah, so I walked into the lab with them having already done all of this work, and then what I did is I helped streamline the process of them making these scaffolds. So there's not pictures of it here, and I didn't find a article quickly, but what they did later with this article or with this research is there were two different pieces. So this is only one of the pieces, and then they had another piece that was on top of it or was it? There's another piece on top of it, I think that was like flat, and there were two different pieces, and they wanted to stick them together with plasma treatment. I'm not super familiar with the physics of it, but basically it's like you put it into this like physics machine, and then you can stick two pieces of silicone together. One thing that's difficult though is these are really tiny. So I don't know if they have a picture in the mouse of how small these are. No, but I mean, they're probably like the width of my finger. And so it's really difficult to align the two pieces together in the plasma treatment. And that was a part that would be tedious in the process. And so what I did is I created molds. I created another mold, or I don't know if that'd be the right term, like template, such that at the edge, it kind of works like Legos where I can get the two pieces to fit together, the two PDMS or silicone pieces to fit together. So these silicone pieces will shrink a little bit right after you remove them from the molds. That's just how the silicone material is. So then I wanted to create a mold of the slightly smaller shape. So I looked at a microscope and I measured how big the silicone pieces were, and then created a piece that looked like this, but was to the new size that was a bit smaller. And then another shape that was the negative of the top piece. And then, like I was saying, like put holes in the sides such that the two plastic 3D printed parts would fit together kind of like Legos. And so instead of like needing to tediously like tweezer one part and like look at it very closely to try to align it, that you would just have like one piece and another piece, and you would just like fit them together like Legos, if that kind of makes sense. Yeah, so that was one project that I worked on over the summer, and it was nice. It was a really nice introduction project, and I got to learn a lot about what the lab does. Cool. Okay. So are there hay algunas preguntas sobre eso? O, si no, entonces puedo continuar con otro proyecto.
No, no tenemos preguntas. Puede continuar, por favor.
Okay, okay. ¿Alguna pregunta siguiente que les interesa más?
Tejido artificial, por favor.
Tejido artificial? Okay, cool. So for my undergrad lab, they do muscle regeneration. Let me see if I get, where's the website? Did I exit out? I might have. Okay. Okay. Hay esta condición en inglés se llama volumetric muscle loss. Básicamente, cuando personas like so in different trauma accidents, so like someone who's military, or maybe cuando hay un accidente de coche, just yeah, there's like a bomb or something happens like collision wise in which you're just missing a piece of muscle. So yeah, say like, or yeah, there's certain types of cancer too, I believe, where doctors will just have to excise a big piece of muscle. And that affects the patient greatly, because then they're just missing this piece of muscle, and like their arm or whatever part of their body isn't able to move well in that way, or can't become strong. And so una de las ideas en como tal vez podemos curar esta condición es por tejido artificial. Como tal vez podemos usar las células de una persona, ponerlos en un scaffold, y entonces podemos poner este scaffold con las células en su cuerpo y esperamos que el músculo va a regenerar. It's like a bit sci-fi. It's not very close to actually happening in reality. But that's also like the cool thing about research is it's like, okay, you can have this crazy idea and maybe you can show how close you got to what your goal was. So the 3D printing part here is pretty simple. Basically, these, what would I call them? Frames are what we called them. These frames were 3D printed based off of how we wanted the scaffold to be of a particular length. Así que otra vez empezamos usualmente con, pues después de hacer investigaciones en algo in vitro o como algo con células que no es un organismo total, entonces podemos hacer pruebas con ratones antes de los humanos. Y en los ratones podemos, we can induce volumetric muscle loss by basically doing a surgery and then just taking out a part of the muscle of the rat. And then we can try to see whether, if we put in our engineered tissue, whether that tissue is going to end up surviving. And so we know how much tissue we removed and how much tissue we want to put in. And based off of that, we can create a frame, or just like a piece of 3D printed plastic such that it's the same length. And so, or well, a length that coincides with what we want the final length to be. So yeah, so it was decided that we wanted it to be of this particular length. And there's going to be some waste on both ends on the frame, because we're gonna end up like snipping the part right under here and then right above where the red frame is at the bottom, because the part where the scaffold stuck to the frame isn't usable. And then to take a step back, what we're doing here is electrospinning. So what is it? Fibrin. There's many different types of materials from the body that we could use as engineering scaffolds. And one of them is fibrin. So like in fibrous tissue in our body, there's fibrin, which is kind of like collagen, if you know what that is. I think it's like a protein. And so it exists also, like scientists have made it into a powder form, and then you can mix it with water, and it turns into a gel. And it's an unordered gel. So fibrin, if you look under a microscope, it's like a bunch of little pieces that are kind of long. And so an idea with that, what we want with muscular tissue is we want really long cells. So we don't want to just inject muscle cells into a scaffold of normal fibrin, because then they would just be going in all different directions as the fibrin is going in different directions in the gel. But what we can do is we can put an electric or like a voltage when the fibrin or fibrinogen, I forget, one of them is the cross-linked version. When the fibrinogen is, cross-linking, so that all of the parts of the gel are aligned in the same direction. And then it's stronger in that direction and more resembles what muscle cells could go into, so that the muscle cells are striated and that your muscle works in a particular direction. So for example, like our arm, right? I can like put my arm in this way, and the biceps or the triceps of my muscle are designed to be in that direction. Our muscles are not designed in a way such that I can pull as strong like in this direction as I can in this direction, because the muscles are in they're striated in that direction, if that makes sense. Okay, so going back to the 3D printing and creating this scaffold, so we have there's a voltage applied while the fibrinogen is cross-linking. There's a needle right here where the gel that's becoming cross-linked is like coming out, and then we like apply a battery such that the potential difference is there's a potential difference between the metal in this needle and the metal that's in this bath where the fibrinogen is being collected. And this metal part in the bottom, it's spinning. So this part drops, the fibrinogen drops, and then it goes in a circle and it keeps going on top of each other. And then we end up with this circle of fibrinogen, but we still need to make it even thicker than that. So we cut a part of the circle, pick it up, stick it to the red part of the end of the frame, and then keep wrapping it across each other. And there were a certain number of times that we wrapped it, I think like 8 times or something like that. And that was how much scaffold that we needed to end up putting it in the mouse. And yeah, so this was a cool project. So after having the scaffold, we would put muscle cells on top of it, and hopefully the muscle cells would infiltrate into the scaffold. And then we would leave it in like a sugary Gatorade water, so that the cells would proliferate and survive. And after the cells had matured a bit, you would put it into a mouse in which volumetric muscle loss was induced. You would leave it in there for a period of time, like a few weeks or something. And then you could take out the entire tissue and see how it performed. So this is what that looks like. So after taking out the tissue, you find that the muscle cells survive somewhat well. So this MHC is some sort of muscle stain. This is what the normal muscle looks like. And this is what the muscle that we had put in through the scaffold looks like. And if it hadn't survived, then this whole part would be black because the muscle proteins would just not be very good, or yeah, they would be like a lot less dark of a green. Well, they might, it's just some sort of muscle protein. It might still be green, but it shouldn't be blue. So DAPI is a nuclei stain. And unfortunately, the difficult thing with engineered muscle tissue is that it's difficult to get the tissue to be exactly what it was before, right? Because this tissue is just so much different. We've put cells into a scaffold and then put that into the body. And yeah, the cells have to be very similar to the original organism if that organism isn't going to reject the cells. And so a lot of times what we'll do in research, because we don't want to use, because it can be easier to get stem cells that are from a different organism, or yeah, like a different individual than the specific mouse that we're testing on, we'll use an immunocompromised mice that won't attack the cells, the foreign cells that we've just put in its body. And then we can hypothesize that maybe if we did use stem cells from the same individual, that if we were to use these same processes, that it would work. And if it doesn't work when we're using this whole method of immunocompromised mice and stem cells from a different individual, then that's indicative of something's not working that maybe we should change. Like maybe we should be switching the scaffold that we're using. Maybe we should be well, changing the scaffold in some way, whether it's making it a bigger scaffold or a smaller scaffold or a longer scaffold. Or maybe we just need to try different methods altogether. And so, yeah, so we would hope that this would bring back function in the mouse. And they had the mice like run, and that also helps like bring, I think, vasculature into the muscle tissue. And so like the legs of the mice did function after putting the engineered tissue in. And then I'm guessing that this is a model in which they like didn't put the cells in, but looks like the scaffold would have been here. And so maybe this is what dead one, yeah, one without cells, but just the scaffold looks like. Cool. Okay. ¿Algunas preguntas o quieren hacer otro proyecto o no sé cuándo quieres terminar esta conferencia?
Ah, no tenemos preguntas, todavía nos quedan 20 minutos. ¿Nos podría mostrar no, ¿nos podría mostrar la de cirugía de la cadera, por favor?
Sure, sure. Let's see. Okay, yes, this paper is this one. Cool. So this was another undergrad project I worked on. A bit different than being like a traditional researcher in a lab, in the sense that this was more teamwork and more undergrad led instead of being under a graduate student. We were mentored by a graduate student, but most of it was led by us. Okay. So with hip surgery, is there an image here of it? Okay, maybe we didn't show a great image. With hip surgery, a problem is that, so basically, well, there's multiple types of hip surgery. We're talking about hip replacement surgery here. So over time, when a person becomes older, there's probably certain indications that would suggest that like certain types of people are more likely to get this than others, but the main one is age. You don't really see this in younger people. Is that over time, the socket of your hip can become worn down. So usually there's like nice cartilage there, and like cushiony material. But yeah, over time it might wear down and then that cushiony material might go away. And then it like hurts to use your hip or to walk when you have bone-on-bone contact between the top of your femur and your hip socket. And so what they do is they replace that part of the joint with materials such that you don't feel the pain in between your two bones. But a difficulty with putting titanium and other materials here and trying to replicate what the hip was like before is that you're not sure if there will be leg length discrepancy. Así que es como el cirujano necesita mirar muy cercamente si está haciendo la cirugía de una manera y poniendo los materiales de una manera que the adjustments like are very close to what the leg was before, because a lot of times someone can end up with a leg that's a little bit longer than the other one due to the surgery. And that's something that patients aren't very satisfied with. And it can also cause difficulty walking and other health issues. And in worst case scenario, it doesn't happen super often, but in worst case scenario, the person needs to redo the whole hip surgery. And so with this project, we were trying to see if we could measure the leg length of a person interoperatively durante la cirugía para que la persona no necesita tener una discrepancia entre sus piernas después de la cirugía. Okay. So here's kind of showing what part of the hip surgery is like right now. So you'll start the procedure. The surgeon will assess what the initial leg length is, insert the implants or the materials, assess the new leg length, kind of just by like trying to line up the patient on the table and seeing whether their legs are about the same. But it's difficult to do. There's different types of ways to do hip surgery. You can go through the back or like kind of through your butt and have the patient laying on the table on their side. And so their top leg that they would be operating on is like kind of slanted down a bit. And so you're trying to estimate how much the angle of that leg is slanted down in comparison to the leg that's more straight because it's laying flat on the table. Anyway, point being, there's a lot of room for discrepancy. There's another way to perform hip surgery, and it just kind of depends on the surgeon which one they do, is to lay the person flat on their back. And so in that one, it probably is a bit easier to assess leg length because both of the legs are laying on the same way on the table. But I believe more people do it on their side, and that's why this is an issue. And so what we were proposing is using a medical device in which so that these two steps would stay the same. The procedure starts, they measure the initial leg length. But after inserting the implant and measuring the new leg length using our device, that they would be able to find a leg length discrepancy and then readjust the implants and insert them such that there's higher chance that after the procedure ends that there is no leg length discrepancy. So if they know that there's a leg length discrepancy, then they can like drill a bit further into the hip, or they can drill a bit further into the femur by taking away more material, or they can use bigger implants if they need to add more material. So what we were proposing is to basically try to create a fancy ruler. So you can determine distances between certain anatomical points and then infer from that because the distance between anatomical points in a few different directions is the same, that the final leg length is also going to be the same. So at first we started using a leap motion controller, which is like a gaming controller, and it'll determine with high accuracy where the points of your fingers are. So we just wanted to test with infrared technology whether this is something that would possibly work. So infrared is like a wavelength slightly outside of the visible light spectrum. So in the color spectrum, we have like red to violet, right? So slightly more than red that we can't see is infrared radiation or light. And we were thinking that we could use this as a way that cameras can detect this particular type of radiation, and it's like kind of like heat. So things that are hot, like it'll detect, depending on which specific wave range we're using. And that, well, okay, so it tracks, that's the way that leap motion uses infrared radiation is, yeah, like the heat from your hands. And then mapping that to them knowing that, okay, hands like have 2 joints on each finger, and then just knowing from the position of your hand what, yeah, the position of each of those joints on your finger is. Yeah, it's like kind of a fancy algorithm, but for some reason it works pretty well. Like you can just put 2 fingers down, and then you can copy the coordinate system in millimeters that it has for say like your 2 fingertips, and it measures with pretty high accuracy what the distance between your 2 fingers is. And so in the case of hip surgery, it's like, okay, so maybe I would want to put my finger on a particular point on the hip that hasn't been drilled out, and then another point on the femur that hasn't been drilled out. And I want to see what the distance between those 2 is before the surgery and after the surgery. And obviously, like the leg could move, and so maybe the distance between those points would change even if there wasn't a leg-leg discrepancy. So if the leg was like this and the hip was over here and the leg was over here and there was an implant in this joint part, like, okay, so if I'm measuring the distance from here to here, but then like the leg drooped a bit since I inserted the implants, this distance is going to slightly change. But if we create a point cloud, or like we have enough points on the hip and enough points on the leg, we would hopefully be able to do the math in determining that the overall leg length hadn't changed. So after doing initial tests with the leap motion controller and our fingers, which this was created for gaming actually. So you can like put this on like a VR headset and use your hands to do certain things in games that they, I believe that there's, games like associated with this thing, with this motion controller. But it's difficult to develop with because they have like a proprietary software that you can't mess with too much. So we just had to manually copy what the coordinate system was here. But okay, so the next step that we wanted to do was try to like copy leap motion, but then be able to use it for our application in hip surgery, and be able to to use it for application better. And so basically we wanted to copy leap motion as much as we could in the technology that we cared about, I guess. So similar to what it was, we had 2 webcams, and then actually the webcams that we have in our daily life, like the one that you're looking at me through, has the capability of seeing infrared. But there's an infrared filter on the camera such that that's why like the way that you see me on this webcam is similar to if we were talking in person. But you can remove that infrared filter, and then the camera is able to see infrared wavelengths. And so that's what we did. We bought webcams, and then I did the research to find this out, which was nice because then it was like we didn't have to buy super fancy cameras. We just had to buy like normal webcams, and decompose them, or take the different components apart so that I could find the filter and remove it. And then we wanted to add a visible light filter to the camera to try to differentiate what was a infrared signal versus what was a visible light signal. And then we had like basically a big flashlight here that we created with the breadboard of infrared wavelengths. So we were emitting light. It was bouncing off of, we determined instead of using fingers that it would be more precise if we were to use a pen. So we created this pen, which doesn't draw, but well, I guess it could draw through the camera, but yeah, it doesn't like create markings on the anatomical bone. And then we put these reflective balls on it so that we could create an algorithm that would know where the center of this plane was, and then there's a fixed distance between the center of all of these balls and where the end of the pen tip is. So by having a infrared light that is shining on each of these reflective balls, and then that the camera and our algorithm is able to detect the center of each of the balls and the center of all four of them, and know which direction the pen is in, we can determine what the coordinates of the end of the pen are. So here was a testing setup that we had. So we printed a grid of 1 centimeter squares so that we know, yeah, like, okay, so the distance between one square and the next square should be 1 centimeter. And then when we measure that again with our pen, does it measure the same distance or is there a certain uncertainty? And this is what we found. So using, let's see, using the IR webcam that we created versus Leap Motion, it's pretty similar comparing the true distance that we know by printing it on the grid versus the measured distance within the range of distances that we care about. So yeah, like 10 centimeters is probably the longest that we're going to be measuring between the hip and the femur. And so yeah, this is kind of just what the picture looks like with the infrared camera and the filter placed in the setup that I showed you before. And then the pen, so then we created an algorithm such that yeah, we could determine, it would detect the circles that were in the image, and then yeah, create a plane and determine where the center of those circles was and where the end of the pen tip was. So going back to how this relates to 3D printing, this was a 3D printed part, or 2 different 3D printed parts. So we printed the frame, and we just copied a frame from another orthopedic surgery lab that our advisor suggested, and so we gave credit to them who created this frame. Basically, they did certain measurements and tests to determine that for orthopedic surgeries, or yeah, for some application that was pretty similar to ours, that this is an ideal configuration of the balls in a frame to determine what the final distance is. Like you could make a bigger frame, for example, but the accuracy might go down, or maybe it goes up, but then it creates a more bulky frame. We believe that with this frame, we would have the accuracy that we needed. And then the part that we custom created was this pen. So yeah, we just kind of arbitrarily chose a distance between the frame and the end of the pen, in that, you know, you didn't want it too long so that it would be too bulky, but you didn't want it to be too short such that it would be hard to use. And so it resembles pretty close to what like an actual normal pen is in everyday life, I believe, just thinking that that would be something that's ergonomic. And here was also one of our older iterations, I think, that I created. I thought maybe that having the handle of the pen separate from the actual pen might help with the ergonomics, and I'm not I'm not super sure slash like don't remember why we decided to take the handle off. It might have been harder to print or it might have not made too much of a difference. But that's just part of the prototyping process. But yeah, it's like you're not sure which design is going to be the best. You might test that one design is better than the other and determine it that way. Or you might go to your stakeholders. So in this case, like going to the surgeons and like asking them which one they like more. Um, yeah, or like some combination of the two. Maybe you work with surgeons to see if they can perform a hip surgery in the same amount of time. With particular designs, maybe some designs take longer to do the measurement for some sort of reason. And then the hospital as a stakeholder kind of cares about that because surgeries are a business in which they want the most surgeries in the minimum amount of time. And so if you're adding too many surgeries, or if you're adding time to each surgery and then they can't complete as many, then that's something that they care about. So that was something that we cared about as well, because if you want our design to be implemented, it has to work into the workflow of a hospital. Yeah, so that's a summary of that project. It was super fun. One of the favorite projects that I've worked on. I love medical devices and had lots of opportunities to present at conferences and design competitions and get different people's feedback in business and also in medicine. So cool. ¿Hay algunas preguntas con eso? I don't know if I can cover the next project in 2 minutes, so hopefully, espero que ustedes hayan aprendido algo hoy.
Bueno,
Sí.
me comentan que no hay ninguna pregunta. Primeramente me quiero disculpar por los problemas con el audio. Es que tuvimos problemas técnicos aquí, así que por eso se escuchaban las voces, pero sí estábamos aquí viendo la conferencia, ¿no? Y también pues agradecerte mucho, Hanna, por tu tiempo y por haber aceptado mi invitación para darnos esta conferencia.
Of course, of course.
Y pues te vamos a entregar una constancia. Aquí rápidamente la leo.
Oh, thank you.
La Facultad de Ciencias Químicas y pues el Club de Robótica Spider te entregamos un reconocimiento por haber participado en este Fest Educativo Spider y pues con tu conferencia Diseño 3D asistido por ordenador para dispositivos médicos. Y pues muchas gracias, la verdad.
Thank you. Gracias a ustedes por escuchar.
Sí. Y bueno, te despedimos con aplausos. Gracias.
No puedo oír, pero gracias. Okay.